Long-sought gravitational wave background discovered. Researchers working on the NANOGRAPH, North American Nanohertz Observatory for Gravitational Waves, project have announced the discovery of the long-sought gravitational wave background, a low-frequency vibration of spacetime. The likely source of the new discovery is the combined signal from multiple pairs of supermassive black holes. Albert Einstein first mentioned gravitational waves in his General Theory of Relativity, published in 1916. He predicted that waves emitted by massive objects moving at high speeds propagate through spacetime, causing distortions, somewhat like ripples on the surface of water. However, the first detection of gravitational waves occurred 99 years later. They were detected in September 2015, but the information was only released after a thorough analysis of the data, in February 2016. The first detections of gravitational waves were made using the ground-based LIGO and Virgo detectors. They involved the collision of two black holes, but in subsequent years, waves originating from the collision of neutron stars were discovered. Astronomers estimate that events that should trigger gravitational waves are numerous and occur relatively frequently throughout the cosmos. This means that such waves constantly create ripples in spacetime, and it is these ripples that constitute the so-called gravitational wave background. Now, several teams of scientists have reported the discovery of low-frequency ripples in spacetime, so-called nanohertz gravitational waves. The discovery was made by tracking the changing distance between Earth and pulsars in our galactic neighborhood. This revealed how the space between the two objects is stretched and compressed by passing ripples in spacetime. For the past 15 years, we've been on a mission to find a hum of gravitational waves reverberating throughout the universe, washing over our galaxy to warp spacetime in memorable ways, says astrophysicist Stephen Taylor of Vanderbilt University, leader of the NANOGRAPH team. We're thrilled to announce that our hard work has paid off and we have exciting evidence for this gravitational wave background, he adds. Pulsars are incredibly dense neutron stars. They owe their name to the beams of radio waves they emit from their magnetic poles. These beams travel through space like a lighthouse. Some spin hundreds of times a second, others even more frequently. Because pulsars spin with such frantic speed and regularity, astronomers can use them as the cosmic equivalent of atomic clocks. Such precise timekeeping helps scientists probe the nature of spacetime and measure the masses of stellar objects. The first detection of gravitational waves came from the collision and merger of two star-sized black holes. The most likely source of this latest discovery is the combined signal from multiple pairs of much larger black holes, millions, even billions, more massive than our Sun. The detected waves are thousands of times stronger and longer than those detected in 2015, reaching tens of light-years in length. In contrast, the ripples detected since 2015 are only tens or hundreds of kilometers long. You could say that the Earth is vibrating because of gravitational waves that sweep across our galaxy, says Scott Ransom, an astrophysicist at the U.S. National Radio Astronomy Observatory who is also involved in the NANOGRAPH work. The astronomer emphasized that he and other research teams are not entirely confident in their findings. Each group has seen hints of the expected gravitational wave signature, but without the statistical certainty to indicate a discovery. Scientists consider a discovery to be made when the sigma value is 5 or higher. Sigma is a measure of statistical certainty. A sigma of 5 means that the probability that it is some random event, fluctuation, or interference, rather than a genuine observation, is 1 in 3,500,000. Researchers reporting the new discoveries reported detections at between 3.5 and 4 sigma, indicating greater than 99% confidence that the signal is real. The scientists will now combine their data to see if they can collectively reach the 5 sigma threshold. If this is confirmed, we'll have 20 years of work to do to study this new background, says Monica Colpi of the University of Milan Bicocca. It will put an army of astrophysicists to work, she adds. 3 teams of scientists have reported similar results based on the analysis of decades of pulsar data. These are the North American NANOGRAPH Group, the European Pulsar Timing Array, which includes astronomers from India, and the Parkes Pulsar Timing Array in Australia. A fourth group from China, the Chinese Pulsar Timing Array, claims to have found a similar signal using only 3 years of data, thanks to the exceptional sensitivity of the FAST telescope. The NANO graph results have been published in 5 articles in the astrophysical journal Letters. The European and Indian teams' findings will appear in Astronomy and Astrophysics. The Australian team submitted their research to the Astrophysical Journal Letters and Publications of the Astronomical Society of Australia. The Chinese team published their work in Research in Astronomy and Astrophysics. Each group relied on a slightly different dataset. NANO graph monitored the most pulsars. The European-Indian team analyzed the longest collected dataset, and the Australian team was the only one to observe pulsars in the southern sky. We are confident in the result because we all see the same thing, says Michael Crame of the Max Planck Institute for Radio Astronomy. All groups use sensitive radio telescopes to monitor millisecond pulsars. Each time a pulsar spins, its radio beam travels toward Earth and beyond. These emissions occur at regular intervals. Millisecond pulsars spin the fastest, up to several hundred times per second. We can use them essentially as clocks. Small changes in the arrival time of the pulsar signals could mean that the space between the star and Earth was altered by the passage of a gravitational wave, says Andrew Zeek of the Australia Telescope National Facility in Sydney. Conclusions drawn from studying a single pulsar would not be sufficiently reliable. Therefore, each team monitored dozens of these stars. To do this, the researchers had to rule out numerous potentially confounding signals from the observed sources, radio interference from ground-based and satellite technology, scattering of the pulsar's radio beams by surrounding gas clouds, and small random variations in the rotation of the pulsars themselves. The LIGO and Virgo detectors are sensitive to millisecond waves produced by single mergers of black holes or neutron stars with masses tens of times greater than the Sun. The results obtained by synchronizing the signals from pulsars instead represent multiple waves, each years or decades long, overlapping in the cumulative background noise. Each wave is generated by a pair of supermassive black holes somewhere in the universe, whose host galaxies likely collided and merged. Imagining the universe as a roaring ocean of space stretching and compressing is incredible. Supermassive black holes are cosmic behemoths at the hearts of galaxies, feeding on gas and disrupting star formation. I look forward to a future in which our observations of pulsars reveal a complex map of gravitational waves radiating from pairs of supermassive black holes. We should see a background noise universe with specific hotspots of gravitational waves from individual pairs of supermassive black holes within galaxies that we can identify, explains Daniel Reardon of Swinburne University.